Thank you for this introduction. So thanks a lot. Many thanks to the organizer for organizing year after year. Fantastic meeting. It's always a pleasure to be at Santa Cruz. I apologize for this very long title that I come up with. So basically, what happened in a cosmic morning for star-forming clumps. And I would like to thank also Aaron for the fantastic introduction he gave, which allows me to save a few minutes on my motivation, showing again this very nice picture, I think the first one from the university, which has been analyzed in great details, as Aaron showed, with the power of gravitational strong lensing. You can see really all these clumps, star clusters that are being formed in this high redshift, so 1, 2, maybe 3 galaxies. So what has been done by Adele Crescent and collaborator from this sample is to put the properties of these star clusters in terms of stellar mass and effective radius, as radius we prefer, and they put them in the plots that I simplified a lot. I remove all the arrow bars, etc., to make it a bit more readable for this argument, and just kept different colors for different redshifts. What we have learned from that is that even at this redshift, the star clusters still obey this zone of avoidance, meaning that there are no stellar systems, star cluster, dwarf galaxies, giant elliptical galaxies, more compact than this line, for which we don't have an explanation yet. Then they went ahead and of course, fitted the relation defined here. And what they did from that is to connect this to what we have known in the local universe. So I picked up another paper and put the two dots at the same scale with the same scaling for the x. So here in the bottom left, you have local universe, old evolved globular clusters in Milky Way nearby galaxies, and even open clusters here in the gray dots. So if you include the open clusters in this analysis or not, it will change a bit the details, but long story short, we could have this type of fitting relation there. And if we compare the two, what we have is not the same relation. There is the same slope between the two, between high redshift and local universe, but with some sort of offset by a factor of 6, if I put it right. So the question I'm asking then is, what happened? Why it's not the same relation? Is there a smooth transition to go from one regime to the other, or is there a sudden break? And if it's a break, then what's the physical cause? What redshift is happening? So one of the keys to solve that, maybe, is to look at, as Aaron said, clumpy galaxies. And knowing that most of these galaxies around cosmic noon host huge, massive clumps in the gas, and they shine in UV because are forming stars. So we noticed since then that the clumps are found in galaxies with a high gas fraction. And for the rest of the talk, I will use this definition for the gas fraction, mass of gas divided by total baryonic mass. And with theoretical studies on these clumpy galaxies, we know that these clumps could play a role in the formation of the thick disk via the injection of turbulence, to maintain high level of turbulence, the bulge with radial migration and assembly in the center, and also, as I said, the formation of globular clusters. I think it's fair to say that these points are still a bit debated, but I think we're getting closer and closer to actually close the debate and think that, yes, they do play a role in all these aspects. So to go in this direction, to try to understand better what's going on and how we can connect these clumpy galaxies to present-day giant molecular cloud, for example, what we did with Oscar Gertz and Alessandro Romero was to run a series of isolated simulations. We want to have control. And if you want to do that, you have to give up, you have to sacrifice on the cosmological context. So no gas equation, no mergers, but I choose the parameters I want for my isolated. So we did a Milky Way mass galaxy, and we put 10% gas fraction. So for the Milky Way, that corresponds to redshift 0 condition. And after some evolution, what you find is the appearance of these structures that develop, and if you squint, you can even see some structures. Nothing new here, nothing surprising. Then what we did was to play with this simulation and to change one parameter and one parameter only, which is gas fraction. So here I'm showing another example when we have 40% gas fraction. So for the Milky Way, 40% gas fraction, that corresponds to redshift 2, 2.5. So clearly, this is not an early stage of that because I conserved all the other quantities, like the galactic mass, like the size of the disk. I only changed one parameter. So that gives an idea of what these parameters, the gas fraction, does. And what you do when you increase it is you give more dynamical weight to the gas phase, to the dissipated phase. It turns out it's molecular phase that changes the regime of instability. So instead of creating spiral structure like that, I'm getting clumps with some sort of elongated structure, but clearly not spiral. So this means that if a galaxy is evolving from a gas-rich stage to a low gas fraction, then we will have a transition between a clump-driven of instability into a disk-driven regime of instability, the one you see in textbooks tomorrow. And we found by running many simulations that this transition occurs at a gas fraction of about 20%. Don't ask why. We still don't know why it's 20%. We still don't know why transition is so sharp. We're working on that, but it's kind of tough. Long story short, this change, this fundamental change in the instability of your disk is what explains what have been coined as valiant disk instabilities. And so that has been around for quite a while now. But more recently, Near and collaborators propose a scenario when turbulence compression coming from cosmological context will favor that. So I think it's very interesting, and as soon as there is compression in something, I love it. But what I want to point out is that you can have the formation of clump without cosmological context. So this can be favored, but it's not necessary. This evolution in the morphology, we also seen it in the kinematics, the work by Florent Renaud when she used different simulations, putting the gas fraction versus the vertical velocity dispersion of stars at birth without any evolutionary effect. So these are two simulations of gas-rich, clumpy disk, which provide high velocity dispersion to young stars, something like 25, 30 kilometers per second. But that's only true above this 20% gas fraction. Below that, we quickly drop to more classical usual value found in the local universe of a few kilometers per second. So then, if you take a step back, what happened after this transition at 20% gas fraction is that you get less turbulence in your galaxy. You get the onset of this disk instability, the two more textbook cases, and you get low and slow star formation, and all this leads to an enrichment at low alpha over Fe. And if you notice all these 4 points, they are the tracer, they are basically a definition of a thin disk, as it has been observed with Gaia and spectroscopy surveys at Apogee, for example. So this means that if you have a high gas fraction in your disk, you have a different regime of instabilities that act all together in terms of kinematics, morphology, chemistry against thin disk formation. So knowing this, next question to ask, is one we ask, is are these differences amplified or mitigated by environmental effects around the planet? So here I'm showing the gas structure for three cases, a 10% gas fraction, 25% gas fraction, and 40% gas fraction. And the first thing we did was to bin these cases in regular grids. Much finer than this one, right? This one is just for illustrative purpose. But what we did in every of these cells was to measure the gas density on the x-axis and some physical quantity I will show later. This physical quantity will be a bit difficult to interpret if I show you the raw value. So what we did was to normalize these quantities to the values they take in the gas-rich case, 40%. So let me give you an example with the Mach number. In every of these cells, at 120 parsec scale, I can measure the Mach number, the level of turbulence. And you see that in 25% in red, it's quite close to the 40%, quite close to unity when I normalize it. It's a bit weaker in the 10% case and low gas fraction. So turbulence is indeed higher in gas-rich disk, as has been observed. This is not so surprising also. So then we went ahead and looked for other disruptive mechanisms that you can think of in galactic disks. We looked at the tides, and to have a fair comparison, we also normalized by cell gravity of these cells, so that's the open symbol. We look at the shear, and again, a version normalized with cell gravity. So this plot is becoming quite complicated, but if you summarize it, you find that we have similar trends for the tides and the shear, but maybe with stronger differences than or the turbulence. So even if you normalize to cell gravity, we have, again, many differences that occur when you pass the threshold of 20% gas fraction. We have stronger disruptive agents in gas-rich disks. Basically, all the red points are above the blue points there. So if disruption is stronger in a high redshift disk, does it mean that you have a shorter lifetime for the massive clumps? Would make sense, right? But not so fast. Give me a few minutes, and I will show this is not true. So after doing this kind of Lagrangian approach, and we move into more structure identification, and we define clumps. Defining clumps and detecting them could be an entire talk, or even an entire lecture series, because you have to make a lot of decisions. So what we did was to consider that we are not so much interested in the absolute values of things. Like here you have Mount Whitney, which is the neighbor in that direction. Do we actually care to see if this forms very differently from that? Maybe not. I think it's not all about the height, it's more about the prominence. And here what you see in Iceland, you have this fantastic peak there, which is like 4,000 meters shorter, but much more interesting when it comes to the formation. So this is why we have a detection method based on overdensities and not on, for example, molecular content. And we also do that because we are going to compare different metalicities, different redshifts. So we don't want a dependence on the metallicity. I can think of another example when you have this high peak with a very high Fe content, but clearly there is not the same formation mechanism between these cases. So with this arbitrary definition and way to measure things, we can plot the clump mass function, the gas clump mass function. Here, that's what we have for the three gas fractions I've selected. And of course, the one thing you have to do is to plot Paulo's fits. What you find is that the two gas-rich cases are very similar, and the one at low gas fraction is actually a bit steeper. Again, a transition at 20% gas fraction. Then I went ahead and fitted, as you see the dotted line, a Schechter function for Paulo multiplied by a declining exponential. I only found a good fit for 40% gas fraction, but I will not say anything more about that because we could have statistical effects. We are not sure we are properly sampling the high mass sense. It's a very interesting problem that we face in this case and also in observations of the cluster mass function, the stellar cluster mass function for globular clusters. On top of that, you have to be careful about subclumps if there are the interstellar medium is hierarchical, and you could have subclusters that form in different parts of your massive clumps, merge together, pollute each other, etc. All this is probably much more messy than what the simulations can capture. So I will not say much more about that. But maybe you are thinking now that everything I'm telling really depends on the subgrid recipes that I adopt, and you're right. The question is how much. So to quantify that, what I did was to go back a bit in time, restart the simulation, and change the parameters that I use for the subgrid recipe. So here you see I multiplied the star formation efficiency from 10% to 30%, and then I divided by 10%, sorry, by 10 to reach 1% efficiency. And this gives me this colored shaded area for the three gas fractions. What you see is that you don't have a lot of overlap between the shaded area, just really at the high mass end when you have a statistical uncertainty. This means that changing the star formation efficiency in that manner does not affect the conclusion of the result as much as changing the gas fraction, the color in this plot. I continued this with the feedback, multiplying the energy of the supernovae, switching off all the pre-supernovae effects like winds and radiation, and switch off feedback altogether. And again, this gives me a shaded area, but which are still much more narrower than the separations caused by the gas fraction. So this is why I'm confident saying that the gas fraction did play the biggest role in the formation or maybe survival of massive clumps. So this means that I can use these clumps I detect and look at their scaling relations. For example, the mass, density dispersion, and size. In these plots, every point is a clump, a gas clump. And I can fit this expression there. If I was using a definition based on the molecular content, that would be exactly the Larson scaling duration. But because I'm using some sort of over-density criteria, it's not. It's actually shallower than the observed empirical relation. But this allows me to compare the case at a low gas fraction, so kind of redshift 0, intermediate gas fraction, redshift 1.5 or 2, and high gas fraction, redshift 2 to 2.5. What you see, and if you look at the numbers I put on the slopes there, is that the gas-rich cases, the clumps in high redshift gases, follows Larson-like scaling relation. We don't have really an evolution between these scaling relations. So there is some sort of universality behind that. Means that the clump in a gas-rich high redshift galaxies follows similar universal relation as a local universe did. Except that if you look closely, you see that the range that you take and the scatter around the median relations increases with the gas fraction. So can we connect this with the star formation activity with the aim of connecting that to the formation of some globular cluster? Here I plot the gas mass and the star formation rate, and I see here the difference with the time scale of star formation, so depletion time, and the efficiency of star formation, how much gas you burn into stars. I hope nobody in this room wants to fit relations there, because I had to do it to put the correlation coefficient and the significance. It's really, really bad. We don't really have strong, if any, relations between the star formation indicators and the clump. But then knowing that it's a scatter around the median relation that matters, then I went ahead and came up with a different quantity to look at. So let me illustrate that with this clump right there. I'm going to define the excess mass. So for its size, how much mass above the median the clump has. Trust me, I know I'm an expert of excess mass. So if you look at that, this is what you have of star formation rate, and you can see that clump with an excess mass have high star formation rate. For depletion time, they are short, and for efficiency, they are high. But maybe there is another way to see that. If I looked at excess mass close to 0, so in this colored band, what I see that you have these clumps that span a big range of values here, that take a very different values. And this is not new. We've been saying that in other simulations, and even in observations, when you look at star formation efficiency for the Milky Way GNCs, giant molecular clouds, there is a large pattern of values in normal galaxies. So maybe instead of saying this, I can rephrase that, saying that clumps with an excess mass have no low star formation rate, no long depletion time, and no low star formation efficiency. So just a different way of saying things. And this would lead to relations like this one being tighter for the outliers, or these weird clumps that you find mostly in gas-rich galaxies. Then you might think, well, it's not a matter of density. So this is what you do if you plot the average density of a clump, mass divided by volume cube, by radius cube. And there is some sort of relation, but it's not as good as with excess mass. Here you can see, you can compare the three indicators: mass, no correlation at all; density, weak correlation; and excess mass, quite tight relation between the two. And the reason why, I'm speculating now, but I think the reason why is we have to make the difference between a dense structure and a compact structure. Dense is your mass divided by radius cube, and compact is divided by radius. So when it comes to survival, when it comes to binding energy, this is what matters. It's 1/r. So you are quite sensitive to that if you study star clusters. A compact star cluster will survive for longer. It's more resistant to disruption, and therefore it could be long-lived. So doing this, having said that, maybe, and then I will connect to what Avishai was saying earlier, we could have two lifetime regimes. A short lifetime for these gas clouds, which is for the normal clumps, those who are close to the median relation, it's universal median relation, and they are found for all gas fractions in all my cases, and some long lifetimes for these clumps, which are only seen in outlier clumps, which are much more frequent for high gas fractions. I'm just speculating here because tracking clumps is very difficult. The gaseous structure, they merge, they split, they evolve, they collapse. So it's very, very difficult to come up with a quantitative argument. So to conclude, what I've said today is that we have different regime of instabilities in gas-rich disks, so basically above 20%, that explain the clumpy morphology in this. Clumps, because of this different regime, act as a barrier against the formation of thin disks. You need to burn your gas to form a thin disk. Interestingly enough, galaxy mergers that do the same, and maybe in the Milky Way, the two effects happen at the same time. We have universal scaling relations for clumps at all gas fractions, but we have a higher scatter in gas-rich disks. It means that we have some sort of universality and more outliers in gas-rich clumpy galaxies. Clumps with an excess mass form more stars. They form them faster and more efficiently. Also, we have more disruptive environments, turbulence, tide, shear, in gas-rich galaxies, but we have extreme clumps being more compact, probably being more crispy also than the average. Therefore, that doesn't mean that they have a shorter lifetime, but maybe they're more resistant to disruption. So if there is only one take-home message you can remember, is that we have some universality population of the gas cloud at all redshifts, plus some extreme outliers that are only found in the gas region. Thank you.
Albert? How sensitive do you think your results are for the resolution? The reason I'm asking because there was this paper by Jeremy Finch and company with a super high resolution on clumps, and they found that these giant clumps you find in typical resolutions are made of subclumps. So I don't know if you looked at it or thought about it, but
oh.
Okay.
I looked at it and I thought about it. So I will go back to this map, and I think I picked, it's this clump there, I'm not sure. And zooming in, that's what you do. So same about same stuff. You have the density contours in gray, big surface density contours, and my clump identification in red. So you see that for the most massive one, for example, you get several peaks, because of the interstellar medium is turbulent, it's hierarchical, etc. Another question is, do we care about the fact that this structure is different from differently than this structure? Or what I said, no, I don't care about that. They share a common envelope, the same dynamically coherent, dynamically bound structure. After that, if you care, if you look at pollution, like chemical pollution from this one to this one, for example, different time scale, different hierarchical merging of the star cluster they could form, yes, it's very important. But with this type of simulation, it's barely resolved. So you see an example in this cloud, you don't see it in others. That doesn't mean it's not there. I don't know. So my short answer would be yes, it's important, but as long as you have one coherent structure that you can define as a clump, in my case as an over-density, I think you can do a type of analysis.
More questions?
So in the end, I'm not sure I get whether the message is also that the clumps in the end are candidates for being the progenitors of globular clusters. If that's the case, how do you match with the geometrical, the distribution of globular clusters in the Milky Way and other galaxies and their dynamics, which is not in the disk?
That's a very good question. I think I've tried at least to be careful not to make a direct link to globular clusters, but to mention it now and then, because there are many steps missing between looking at gas clumps and actually found surviving star clusters. It takes a lot more physics, a lot more resolution, also looking at formation of binary stars, looking at two-body interaction and collisional dynamics before we can reach this conclusion. What I can say safely, I think, is that clumpy disk, cosmic noon, won't explain the full population of Milky Way globular clusters. They are only the end of the story, the last stage of the story. The peak, I think, redshift 6 for the formation of the globular cluster of Milky Way, even higher maybe. So this type of mechanism is only marginal for the Milky Way. And on top of that, as you mentioned, then you will have to explain why they end up in the stellar halo. Maybe you could have dynamical ejections, like slingshots on the disk with clump-clump interaction. I think you can imagine that if I show you my other slide here, the movie will guide you through the graphical structure of the disk. You see how messy it is. But also you have to take into account that clumps that would stay in the disk, they probably experience stronger tides, and they will dissolve. So you will only see those who have been able to be ejected to higher galactic latitude. So not explaining all the Milky Way globular clusters, of course, maybe some of them, and maybe a more generic mechanism for clusters in other galaxies.
We have time for a quick one, and the next speaker should approach to the test.
Thanks, Florent, for the enlightening talk. So I happen to know a little bit more about the technical details because I'm running similar setup simulations. So I wonder, because your gas fraction is changed, but it's always in the same disk configuration, if I understand correctly.
Yeah.
So to what extent do you think the universality may come from this same configuration? What if like you have a hot gas to begin with, and let the hot gas halo to cool down into a cold disk? What happens?
That's an excellent question. I'm not sure. I'm really not sure because you have to, I guess, mitigate that with your feedback with different buffing up of the even the circumgalactic medium, basically all the way with more physics. So I'm not so sure how I can answer your question. The approach we followed was to change only one parameter that we can control. So then you lose a bit on the realism. It's not an evolutionary sequence so much. So I guess you need much more precise and much more expensive simulations to precisely answer. The disk thickness will definitely play a role. What we did was we've been careful about that when it came to the instability regimes because we didn't use the razor thin Romeo Q. We used the Romeo and one of the Romeo's Q parameters on the left. When you can compensate for the thickness, you can take that into account. So at least for the instability regime, this is well taken care of.
Okay, thanks. Let's thank our speaker again.